Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is FARIS. So today I will be presenting about my final project with title Winding Slot Improvement Analysis of Radial Field Excitation Coil Flux Switching Motor for Optimal Performance. For introduction, HFSM is upgrade from the PEFSM, which is Permanent Magnet Flux Switching Motor, and also upgrade from the FEFSM, which is Field Excitation Flux Switching Motor. Okay, from the HFSM is Hybrid Excitation Flux Switching Motor is combined flux produced by permanent magnet and FEC located on stator to create the further excitation flux. The operation of the HFSM is exchanging the polarity of the FEC flux linking with the armature coil flux to the rotor position. Okay, the benefit of the HFSM is can improve the maximum torque, power, and also the motor efficiency. Next, we move to the problem statement. The right figure show the one of the HFSM motor. So this is for the armature, this is for the FEC in radial direction. So I will sketch the polarity of the armature and also the FEC. So from this figure show that there is an overlap winding problem between the armature and radial FEC winding. So we can see the overlap between the armature and also the FEC. So from the overlap winding will cause the high coil end to have the higher losses, high flux saturation in flux distribution, and also this overlap will be decrease the motor efficiency. Okay, to prevent the overlap winding, FEC slot and armature slot used to be improved. So the objectives of the project is first to improve the flux distribution of armature and field excitation winding slot of HFSM. Second is to examine the optimal of motor performance in terms of cogging torque, BMF, flux leakage, flux distribution, and also the output torque of HFSM. So this is for the scope of this project. First is the specification of the motor HFSM is based on the table 1. So the outer stator of the stator is 134.5 mm and the radius of the rotor is 97.25 mm. So the rotor angle is 12.8571 and the stator angle is 15. So we fix so in this project we fix the permanent magnet is 1 kilogram. So the second scope is the analysis performance will be divided into two, which is no load and load analysis. So for no load analysis will be analyzed in terms of cogging torque, BMF, flux leakage, and flux distribution. So in terms of the no load analysis will be analyzed in terms of performance torque JE at various JA by using the AHMAD designer. So the related restriction for the electrical maximum is 650 for DC bus voltage, and also the maximum current is 360 current. And for the armature current density JA and the current FEC density JE, we set the 30 ampere. Okay, this is for the part methodology. So this figure show the general flowchart of phase 1 and phase 2. So in phase 1 is more how I design the motor, and in phase 2 is the upgrade or modification of the motor from the phase 1. So in phase 1, I use the geometry editor to design the 12 slot 14 poles of HFSM. So from the design, if the design there is an overlap design, we need to change the parameter. If no, we need to proceed to geometry designer, which is we need to set the materials and condition. And next we proceed to the no load analysis and also the load analysis. Okay, next we proceed to the phase 2. So from the phase 2 is motor modification from the phase 1. So basically I change the armature parameter, which is R7 and R8. If AC slot not around from 168 and 40 mm square, we need to change the parameter, which is R7 and R8. So if the AC slot area around 168 and 40 mm square, we need to proceed to change the FEC, which is R5 and R6 of parameter. So then we move to the load analysis. So we need to analyze the coil gain torque, which is if the coil gain torque more than 9.6 torque, we need to change the parameter of FEC. If the coil gain torque less than 9.6 torque, we need to proceed to the load analysis. Figure 3 show the flow process design of 12 slot 14 poles HFSM. So basically this is from the phase 1, which is we use the geometric editor to design the rotor, stator, permanent magnet, FEC and also the armature. So from the design, if there is an overlap design, we need to change the parameter. If no, we need to proceed to geometric designer to set the materials, conditions, set circuit, set mesh and study. So if finish, if not finish, we need to change the setting. If finish, we need to proceed the quality analysis, and then we move to the zero rotor position. So here zero rotor position, I set the negative 2.2, and then if the angle you face not in 90 until 270 degree, we need to change the initial position until get the in range of the U phase, which is 90 until 270. So that's why I changed to the rotor position into the negative 2.2. If yes, we need to proceed the three-phase arrangement. So this is from the phase 2, which is a flowchart of armature coil and FEC improved HFSM design from the phase 1. So first, I modified the armature coil shape with same area, which is 168.40 millimeter square. If AC slot area not around 168.40 millimeter square, we need to change the parameter. If the slot area around 100, if yes, around 168.40 millimeter square, we need to proceed the APC modification, and then we proceed to the coil gain torque analysis. So if the coil gain torque analysis more than 9.6 torque, we need to change the parameter of FEC. If the coil gain torque less than 9.6 torque, we need to proceed the no load analysis, which is BMF, plug linkage, plug distribution, and also we proceed to the load analysis, which is we need to analyze the output torque. So this is for the complete design of 12 slot 14 pole HFSM. So figure 5 is the conventional design, figure 6 is initial design, and figure 7 is final design. For the figure 6 and 7 is the improvement design from the conventional design. So for the figure 6, I only changed the AC parameter, which is armature in slot area 168.40 millimeter square, and slot area of the APC is same like conventional design, which is 230.55 millimeter square. So in figure 7, which is final design, I changed the AC and also the slot area of the APC, which is in slot area for APC, AC which is 168.40 millimeter square, and the slot area for the APC is 184.36 millimeter square. So this slide shows the figure 7 final design, which is improved design from the conventional design and also the initial design. So in table 2, show the parameter of armature and also FEC HFSM. So based on the table, I compare between the value of conventional and also the final design. So we can see the FEC parameter, which is FEC white, is from the conventional design, is 7.676, and the final value is 6.39 here, 6.39. Okay, next we move to FEC height, which is R5. From the conventional design is 29.98, so the final value is 28.78. Okay, so from here, what I can say, the slot area for the from the final design is less than conventional design, which is 168.40 millimeter square, and the conventional design is 230.55 millimeter square. So of course, if the slot area is decreased, the number of turn of FEC will decrease too. So from 57 will decrease the number of turn, which is 46 turn. Okay, next we proceed to the width of armature coil, which is R7. It is from the conventional design is 6.46 and the final value is 9.434, and the length of the armature coil, which is R8, the conventional value is 26.006 and the final value is 17.85. Both of these value around the slot area around the 168.40 millimeter square, and also the armature of the turn is same because the slot area not really much change. So this is for the flowchart of the coil test. So after we finish the design of the motor, which is HFSM, we need to proceed the coil test, which is we need to proceed the 12 coil test analysis. Then we move to the 3 group coil test analysis. We determine the UVW coil test. If the UVW test not shifted 120 degree, we need to change the polarity or arrangement. So if the UVW coil test rotate the 120, we need to proceed the next step. So figure 8 show the result of the 12 coil test, which is what we can see here, the coil 1 until the 12th coil. So this is for the 3 group, which is U, V, W. Okay, then we proceed to the result for the 12 coil test analysis. So figure 9 show the graph of V flux, figure 10 show the graph of W flux, and the figure 11 show the graph of U flux. So from the graph, what we can see here, the magnetic flux will be generated with the by using the permanent magnet flux as the source for the flux and obtained by each of the armature and FEC. So for the graph of U, I already changed the zero rotor position to negative 2.2, and what you can see, the graph is in range 20 until 270 degree. So now we proceed to the result of the 3 coil test analysis. So figure 12 show the graph of 3-phase system. So basically this graph I combine the UVW phase in one graph. So in this part is to convert the single phase to the 3-phase. So the maximum value of the flux is 0.01243 Weber. So this is for the graph, the final design. So next we move to the result for the no-load test analysis, which is Coggin torque. So the Coggin torque occur when there is an overgap in the machine between the stator and the rotor. So from the Coggin torque, we producing the undesired vibration and noise, and also will be affecting the motor efficiency. So basically figure 13 show the graph of the top beam twin design, which is conventional ignition, and the last one is final design. So from other analysis, final design produced the Coggin torque is 8.2 torque, as lower than the conventional, which is 9.6, and also the initial design, which is 20.6. So basically the final design will produce less vibration, noise, and also will be give the more efficiency to the motor. Okay, next part for the no load test analysis is back EMF. So from the back EMF is the voltage generated in electric motor when there is an electric motion between the stator winding and the rotor magnetic field. So figure 14 show the graph of the back EMF between design, which is conventional, initial, and the last one is final design. So from the graph, what I can analyze is the final design has lower back EMF, which is produced 22.426 volt compared to the initial design which is 42.576 volt, and the conventional design produce 54.921 volt. So what I can say here, the BMF for the conventional and initial design has much of the distortion that can give the effect on lower torque and reduce the motor performance. Okay, for the final design, the waveform for the final design is more sinusoidal, which means less distortion, and the waveform can provide good in practical application. Next, we proceed to the no load test analysis, which is for the flood linkage. So for the flood linkage is the flood wave generated from the permanent magnet, which is there is no current inject into the motor. So figure 15 show the graph of the flood linkage between design, which is conventional, initial, and also the final design. So from the analysis, what I can say, the final design has slightly lower flux with 0.0124 Weber compared than the initial design of 0.0232 Weber, and the conventional design is produced 0.0317 Weber respectively. So the next part for the no load test analysis is the flood line analysis. So figure 16 show the flood line for the conventional design A, B is the initial design, and last one C the final design. So the flood path generated from the permanent magnet, and most of the flood flow at the around of the stator and FEC. So the high flood flow into the rotor cause the high gap density. So this condition will be occur flood leakage and flood cancellation of the flood line. So the flood line from the conventional design and the initial design produce more flood flow through the fault rotor poles. Here we can see the fault rotor poles, higher greater back EMF compared to the final design, which is reduced flood flow at the fault rotor poles, which is result in lower get lower back EMF for the final design. So this is for the no load test term, which is the flood distribution analysis. So from the figure 17 show the flood distribution. So figure A is the conventional design, figure B is the initial design, and the last one, the figure C, is the final design. So from the stator slot between permanent magnet, FEC, and the armature coil slot have a limit space and effect on flood saturation in stator part. So in figure 17A show the magnetic flux density at maximum 1.8932. So beyond this value, the flux will start the saturated, which can be seen at the armature and FEC of outer stator in red scale. So we can see the saturation will start here. So in figure 17, the magnetic flux produced for the initial design is 2.0149. Is better than the conventional design, produce 1.832, and the final design is 2.0057. So from the value, from this value, the flux start saturate, which can be seen at the armature and the armature and the FEC. We can see here between the armature and the figure C also. So from what I can calculate is the initial design is the better of the magnetic density, because the value is 2.0149 will start the saturate compared to the conventional and the final design. So this is for the load test analysis, which is figure 18 show the graph of average output torque versus JA at various JA. So when JA is set between 5 and 10, so the output torque will decrease at JE at 20 ampere. So we can see here the graph will decrease here, and also for the JA5 and JA10. So next point is when JA is set between 15, so the output torque will maintain constant. So the output torque will maintain constant at JE is 25, will maintain constant the output torque. So for next point is for the JA is set 25 and 30. You can see here 25 and 30. The maximum torque we obtain for the 25 JA is 279.48 torque, and the JA30 is produced torque is 292.05 torque respectively. So what I can say from the graph, it is so clear for the JE. For JA, where much flux FEC is generated and the torque is increased, ensure that there is less magnetic saturation or flux cancellation. So this is for the load test analysis between design for output torque, which is conventional, initial, and the final design. So from the previous slide, show the final design for the output torque graph. So this graph show the comparison between the design. So basically for the conventional design, the maximum of the average output torque is produced 295.258 is higher than in initial and final design, which is the initial we produce 273.509 and the final design is produced 292.047 torque. So the last part is part conclusion. So all the objective has been achieved successfully in terms of improving the core gain torque, BMF, flux leakage, and the flux distribution of the HFSM motor performance. So what I can conclude from the final design is by changing the parameter of the armature with slot area around 168.40 mm square and changing the FAC slot area from 230.55 mm square of conventional design to the 184.36 mm square for the final design was proof that can reduce the number of turn FEC turns from the 57 to 46 turns, and also it can reduce the core gain torque of 8.2 torque, also the flux leakage 0.01243 Weber, and the last one is BMF, which is can reduce until 22.426 volt for the silent rotor for 12 slot for 14 pole HFSM. But however, the output torque of the final design obtained 292.047 was lower than the conventional design, which is 295.258 torque. So for the recommendation, what I can recommend is first improve the slot area of the armature to reduce the number of armature coil turn, to improve the core gain torque and also the output torque. Second is change the FEC corner design to the circle design to reduce the stress and reduce the flux cancellation of the motor HFSM. So that's all from me. Thank you. So this is for the part simulation and this is for the design for the final design of HFSM. So first I will show you the flat line. So this is for the flat line for the final design. We can see the Ford rotor has less magnetic linkage, which is from between the rotor and stator. So then I will show you the flux distribution. So this is for the flux distribution. We can see the maximum of the magnetic flux density is 2.0057. Okay, for the data of the core gain torque, BMF, and also the output torque, I will change to the Excel. So this is for the Excel for the core gain torque, BMF, and the flux linkage. So basically, so this is for the final design. This is for the final design. This is for the initial design. This is for the final design. So three of the result are combined in one graph. So this is for the one graph. So we can see that this is for the flux linkage value in maximum. So this is for the core gain torque, the value in maximum also, and this is for the back EMF value. You can see the back EMF value here. Okay, then we proceed to the output torque. So this is for the output torque analysis of the final design. You can see here. And then this is for the graph of the output, which is at various design, which is conventional, initial, and final. So that's all for me. Thank you.